Good morning. We are going to get started today on a new topic. It is AC power. So this is our first lecture about this particular topic. You may have actually noticed by its absence that AC power might be different than some of the other AC topics that we have learned about so far. So just to kind of recap a little bit, what we've done for AC is that we've learned that by converting any of our passive elements to complex impedances and then converting any of our sources to these kind of phasor expressions of those sources, we've been able to use basically all of our circuit analysis techniques that we learned for DC. We've been able to bring them over to AC, with the only kind of asterisk on there being that we've got to work with complex numbers as opposed to working with just pure real numbers. But you may have noticed by way of its absence that we really haven't asked you any questions yet in any of your homework or that kind of thing about power. And the reason is that power ends up being just a little bit different, okay? The reason for this fundamentally is that all the other techniques that we've done so far, we have either been multiplying or dividing, voltages with impedances or currents with impedances, okay? But so far, we haven't actually had to multiply a voltage with a current. And when you think about what happens when you do that, that is multiplying two phasor values together, and it turns out that actually acts a little bit differently than what we would have thought, okay? So we're going to get there, but I wanted to kind of tease with why is it you haven't seen any power kind of questions yet, and it's because it works just a little bit differently, and we're going to introduce that today, okay? Before we get there, let's go back and review material that we covered way earlier in the course, okay? Let's review how do you just find power generally with respect to electricity, right? And you see it up there on the screen. All you need in order to get instantaneous power, in other words, right at an instant in time, all you need to know as far as how much power an element is absorbing is you need to know how much voltage is across that element and how much current is flowing through that element simultaneously. If you multiply those two values together at an instant in time, you will get how much power that element is absorbing at that instant in time. I also wanted to remind us that there is sort of a relationship between the orientation of voltage and current and whether or not you are supplying power or absorbing power. Okay? We typically, unless it's kind of stated otherwise, we usually take absorbing power to be positive. That's our kind of normal sign convention that we use in here. Although if your statement of your problem asks for something else, you want to make sure you give what that statement of the problem asked for. In other words, if it says, tell me how much power something is supplying, you want to make sure that you report it that way. But anyway, how we have a circuit element set up so that it absorbs power is that current flows into the side of the element that has the positive voltage, right? Or if it flips around and current is flowing out of the positive side of the circuit element, that means that circuit element is actually supplying power into the rest of the circuit and not absorbing power from the circuit, okay? So these are kind of some background things. Let's talk about what happens over time now that, because we actually could set up one of these circuit elements that could actually get a varying set of quantities of voltages and currents. And so what I'd like to do is just go ahead and set up kind of a little miniature problem here. Let's say that I've got a chart here that where I've got voltages that are given. Let's say I've got a voltage over time that starts out at 3 volts. You see I'm reading it relative to the left scale over there. And then it drops down to -1 volt. From there, over the next few seconds, it drops down to -3 volts, like this. And then over the next few seconds, it just stays at that value, okay? And let's just stop it there at 20 seconds. Right, so let's say I've got a voltage profile that looks something like that. Now let's do a current profile. Just to kind of make sure you're oriented with what I'm drawing, I'm going to be measuring my currents relative to the scale over there on the right. Okay, so these amps that I'm going to read are measured relative to over there. So let's say I start off at half of an amp like this, And then from there, let's say that I slope up until I get to -1 amp right over here, okay? And then let's say that from there, I just go straight across from here to here, right? And then let's say that I increase up to this point up here. All right, so let's say these are my two profiles for our circuit element, and this is set up so that it sort of corresponds with my standard sign convention. In other words, as I'm showing you this voltage and current, it's being expressed with respect to how this picture is set up over here and not the supplying power one, okay? Just to kind of make sure everyone's comfortable with what we're trying to express here. All right, how do I go about trying to plot power on this set of axes now that I know what voltage is and what current is over time? Okay, and I was kind, I guess, in that I set it up initially over here so that we just had two constant values. Not only that, they're both positive. Okay, so how much power do I have in these first few seconds up to where I have that, first place where the current starts to change? I have 3 volts at 1/2 amp, right? So that's going to be 1.5 watts. Okay, so I'm going to measure these relative, I have it kind of written over here, the power. I'm going to measure these over here on this scale, right? So I'm at 1.5 watts because 3 volts times 1/2 amp gives me 1.5 watts. Okay, now I've got this little slopey line, but this slopey line is being multiplied by what? Okay, the 3 volts still that I have over here on this scale. So one way of dealing with this is to just figure out what it is where it gets to the end. In other words, right here at this point, how much power is associated with that point right there. Okay, what you'll see there is that we get to -1 amp multiplied by 3 volts, and so that ends up going down to -3 watts, something like this. How do I know it's a straight line? A constant multiplied by a straight line gives you a straight line, right? So that's what I'm doing in that little segment right there. Okay, then what happens with voltage? Looks like there's an instantaneous drop, right? And it goes from 3 volts down to -1 volt. What is -1 volt multiplied by, over here I'm measuring relative to this scale, so -1 volt multiplied by -1 amps. How many watts does that give me? 1 times 1, right? -1 times -1. So that goes up to 1 watt. So this goes up like this until I hit 1 watt over here. Then what happens? Right? Now I've got a constant current at -1 amp, and I'm going from this point, where does it end up? Got -1 amp and -3 volts. So that means I go up to 3 watts. One of the reasons I'm illustrating this is so that you can see that if both the voltage and current directions flip, that's what negative numbers mean, right? If both of them flip, meaning, both the current direction and the voltage direction on your circuit element flip, what does that do to power? It means you are still absorbing power in that scenario, right? It's only when they have dissimilar signs, right? That's when it would be supplying power. Okay? Following that so far? All right, and then we have one last segment here. Where does it end up? It ends up where my current goes up to 1 amp, but my voltage is still at -3 volts. So where all does this go? Looks like it's probably going to go all the way down to -3 watts. Something like that. All right, now here's a few things I want to point out as well. And this makes sense, but I want to actually, mention it. Do you notice that the power curve crosses 0 every time that either the voltage curve or the current curve cross 0. Okay? Does that make sense? Well, it should, because we're doing instantaneous voltage times instantaneous current. If either one of those values is 0, you expect power to be 0, right? So you better have crossings of your power curve anytime that either voltage or current cross 0. Okay, so that's kind of the first thing that I want to mention. And I think I already mentioned the idea that if you have dissimilar signs, you're supplying power, right? What would that look like on this chart? It would be everything that is below 0, right? Down here is supplying power, right? And then up above 0 is absorbing power, because that's how I defined my sign convention, was that absorbing was positive and supplying was negative. Okay? Now, let's talk about energy. This is also something we've covered earlier in the class, but do you remember what our equation was for energy over a particular time interval? Anyone remember that? Well, it's kind of what you might think, in that because energy is fundamentally kind of a rate of, power is a rate of flow of energy is what I meant to say. Power is fundamentally a rate of flow of energy. If you take power and you multiply it by what? Time, then that gives you kind of an idea of how much energy, right? That works great as long as you have a constant value for power. You just take that power and multiply it by time, you get how much energy flowed. The thing is, though, that power is not this sort of constant value that happens over a long stretch of time in every case. That's actually kind of a special case where it's just a constant value. So how do we deal with energy absorbed during a time interval? Well, we do it this way. We take an integral, right, from one time to another of what? P as a function of t, where p is power, dt. And what you're really doing there is you're dividing up your time into all these little sort of rectangles, right? And you're adding up all those rectangles over time so that you end up getting how much energy has been transferred. Okay? Now here's another really important question before we get into AC power, and that is, how do I determine the average power during a time interval when that power is not just a constant? It's easy if it's just a constant, right? But how do you do it if it's not a constant? What's your kind of thought process or reasoning that you would want to use to figure out average power over a particular time interval? Well, how about this? What if we take the total energy flow and divide by how much time? Does that make sense as a technique? Okay, so what that might look like, we could do it with two different times like this. I'm going to actually do a form of it that assumes that you're starting at a time 0 and then you're going to a time t of some kind. It's another way of expressing the same idea. But this is just going to be equal to 1 over however much time your interval takes, right, times the integral from 0 to t of p of t dt. So really all it is that you're taking how much energy was absorbed over the entire interval of time and then dividing by how much time that was, and that gives you the average power over that time interval, right? Pretty straightforward. We've already touched on these equations before, but this one's going to be relatively important to us when we get into trying to figure out what happens with our AC power. Okay? Any questions yet? All right. Well, let's move ahead and take a look now at what happens with AC power. Okay, so let's say, I'm going to do a specific example here to start off with. Let's say that you have voltage and current phasors that you have somehow come up with for this circuit element that is, incorporated into some bigger circuit. Okay, I'm only just showing the circuit element sitting there in this case, but let's imagine that that circuit element is implemented in some kind of a circuit, and then we do some analysis on that circuit and we come up with what the voltage phasors should be across that circuit element and what the current phasor should also be through that same element. Okay, and I've labeled those up here on this little element. Before I get into answering this question down here of should the power simply be the product of these two phasors, because that's one thing that would make sense based on or at least at one context, that would kind of make sense to us to just say, well, everything else worked this way with complex numbers. Why don't we just see if we can do the same thing we did with DC, multiply voltage times current, and see if we can get power? So I'm going to answer that question, but first let me just mention what each of these equations looks like if you put it in time domain, right? So like V of x would be what for this first one? 2 volts cosine of what? I mentioned over here what the omega was, so let me put that in, 377 per second t minus 10 degrees, right? That's what my little wave over there that I'm plotting, that's how I would plot that wave, right? Because I need to know some kind of a time value in order to plot that thing. So I would use a time domain statement of it like that. What about for my I value? Ix of t would end up being what? Probably just 1.5 amps cosine of 377 per second t minus 65 degrees. Anyway, I just wanted to mention, if you want to do plots like these, you often have to get whatever your phasor statement is of these values and convert them to time domain so that you can imagine plotting them relative to time. So this is time over here, by the way, and in time domain, the numbers that you see along this axis, in case you're curious, are milliseconds, right? All right, back to the question. Should power simply be the product of these phasors? Let's do that product real quick and see if that makes sense, okay? So the product would be what? 2 volts times 1.5 amps would give me, right? I'm basically taking 2 volts angle minus 10 degrees multiplied by 1.5 amps angle minus 65 degrees. Okay, what does this end up giving me? I think it ends up giving me 3 watts, right? Because if you remember how you multiply two phasors or two complex numbers in this form together, you take the amplitudes of the two of them and multiply those together. Then what do you do with the angle? You add, right? You take the 2 angles that you've got, you add those 2 together, and that ends up giving you minus 75 degrees. Okay? What would the wave look like if that is how this really worked? Right? If it worked like everything else, it's going to have a frequency that is going to be the same, right? If it worked like how our other circuit analysis did, we're not worried about the frequency side of it. It would look like just the same. And we would have a wave that would be centered on 0, right? There would be a wave that would be centered on 0. That's what would be implied by just multiplying these phasors together like this. Well, is that how it really works? Okay. Good news is, if you have a tool, something like MathCAD or anything else that can plot functions, I can take these 2 functions right here and I can just try it out. See what that new function is going to look like if I just take those 2 functions and multiply them together. And let me show you what it looks like. If I take those 2 waves as functions, multiply them together, it ends up giving me that black curve right there. Is it centered at 0? No. Does it have the same frequency? No. Okay. So we're kind of screwed up here just a little bit as of right now. It might not mean that we're cannot use anything out of what we have up here for the phasors, but it's at least obvious, it should be at least, to note that it's not just a straight up application of the 2 phasors multiplied by each other. Let me give you a few notes here that I notice off of this curve, okay? So let me put this right here. I'm going to make some sinusoidal power notes. And I'm just going to do this based on what I see over here on this curve, okay? The first thing that I'm going to notice here, do you remember what our setup was to find average power? We wanted to take kind of 1 over the time for a particular period of time multiplied by this integral from 0 to t. When you have sinusoidal power or sinusoidal shape like this, what would be a very interesting time frame for us to use, right? In other words, this doesn't work for every function, but for a sinusoidal function, if we pick a particular time frame over which to do that average, then that basically means it will work for averages over all time, right? Because this is a repeating function. It's a cyclical function, so it keeps doing the same thing over time. What I'm driving at is if we take one period to be the time frame over which we are going to average, then that means over an average out to infinity, it's going to be the same value, right? In other words, if we do it for one period, then that's good enough to say, well, if it keeps on in this format, then that's going to be the average power forever. Does that make sense? So I'm going to do this with respect to kind of showing the period of the original frequencies, right? What would that look like on this chart? Okay, let's say I start at a period over here, or start at a time 0 over here. Where do I get to one period's worth of a wave for my original waves? Not for my power wave, but for my original waves. Okay, looks like I come down up here, and maybe right in here somewhere is where I reach one period, right? And I'm going to give that a different letter. I'm going to call that capital T. T is what we call period. So if I want to know what my power is going to be on average forever, I can do that by just figuring out what the average power is over one period's worth of, of this wave. And what that would look like over here would be this, right? I would take 1 over the length of the period multiplied by an integral from 0 to t of p of t dt. Furthermore, I can define what that period is in terms of things that I might know for my original waves, like for my voltage wave and for my current wave. I can say that t is going to be equal to what? Okay. For me to go through one entire cycle, that would be 2 pi radians, right? Okay. And so that would be the t value. If you multiply that t by omega, you better end up with 2 pi. So I'm going to divide by whatever omega that is. This is how you figure out what your period is it's 2 pi over omega. Okay, so this is my first of my sinusoidal power notes, is that if you want your average power forever, right, you can just do that by taking the average power for one period. Okay, second note that I would like to make, is this, right? The average power appears to be non-zero. How do I know that? Well, I can kind of interpret what this integral actually means, right? I can say, well, that's going to be the area for this one period. It's this area here, along with this little area here, along with this little area here, and this little here, and then we might end up with a little bit more right over there. Okay? Now, let me make sure we are on the same page as far as what this means, right? Right here, in these upward peaks, this is absorbing energy, right? The circuit element that we're talking about here is absorbing energy during those peaks up there. What happens down in these little deals right down here? I'm going to say it this way. Gives energy back. And because it doesn't give the same amount of energy back as it absorbs, that means that over a long period of time, your average power looks like it's not going to be zero, at least for this particular example that I'm showing you here. Okay? Let me make one other note here. Okay? This P of t function looks like it has double the frequency and an offset. Right? When I say offset, I'm talking about a vertical offset of this curve, but it also looks like the thing has double the frequency. One of the ways that we could have predicted that, just based on our discussion of power a few minutes ago, is that we know that there has to be a crossing of zero power every time there's a crossing of either voltage or current, right? So that means we knew there had to be a crossing here, there had to be a crossing here, there had to be a crossing there, and there. And the only way that that really works is if you can double the frequency so that you can get all those crossings. Okay? Now, I want to show you one other thing here real quick because I think it's also interesting to note. I took a problem that was very similar to this one, and I wanted to show what happens as you change the phase difference between voltage and current, right? In other words, this case, I had voltage that was at a negative 10-degree phase angle and current that was at negative 65. There was a difference in those phase angles on this problem. So I wanted to show what that looks like as we actually change that phase shift angle. Okay, now I did a more general one where I'm starting one of them at a phase angle of 0, but I set this one to almost 75 so that it would be roughly looking the same as our problem that we're working on. Okay, but here's the neat thing about setting it up this way. We can see what happens now with this power curve as I change the phase shift angle between my voltage and my current. You want to see what that looks like? I have this set up so that I can go all the way to where they are perfectly in phase to start off with, right? So no phase shift for either one. They're perfectly in phase. What happens to that wave? Okay, what happens is that it's going to have a certain amount of power absorbed. It'll go down to 0, then it'll go back up to a certain amount of power being absorbed, and it'll do that over a long period of time. Now, without doing really much math, but just looking at the plot, what would you say that the average power should be for this case? And how would you go about trying to think about that? I mean, some of you probably see up here that I'm calculating it, right? So you know what the answer maybe should be. But why? How could you have known that just by looking at the wave? Okay. What if I imagine slicing all the tops of these peaks off, flipping them over, shifting them over, and dropping them down in the valleys? What you end up with is a big old rectangle that would have a height of 1.5 volts, right? Or excuse me, 1.5 watts, right, over all time. Okay, so that would be evidence that that's, you know, a good way to think about that. It's going to be about half of whatever the peak power value is on this wave. Okay, let me show you another interesting thing. What if I take this thing and I shift it over to where we go to 90 degrees of phase difference? Now let me ask the question: is current leading voltage or is current lagging voltage? I'm going to let you think about that a little bit. Is current leading voltage or lagging voltage? Current is the green curve. Voltage is the red curve. Okay? And remember, the further left you go along the timeline, that's earlier in time. So it looks like we reach a peak in current before we reach a peak in voltage. Right? So when we are at a phase shift where, you know, the phase of the current is at 90 degrees and the phase of the voltage is at 0, that says that our current is leading our voltage by 90 degrees. What circuit element is that? Which circuit element has current for sinusoidal AC voltage like this, right? Which circuit element is it that has current leading voltage? You remember? Okay. It's a capacitor, right? If I see a curve that looks like this, then what I have is probably a capacitor, right? And what you notice on this, how much power on average does a capacitor take? Like how much power is absorbed in the capacitor on average over time? 0. And that's because however much it takes in, it gives it back. Okay? And you see it there on that curve. Okay? What happens if I go around here now? I'm going to stop at 180. Okay? See if I can. There we go. There's 180. What kind of a circuit element does that represent, you think? Remember, the wattage number that I put up there is absorbing. So I'm absorbing negative 1.5 watts in this case. And that looks like the maximum value that I get, or maybe minimum value I get, right? The most negative value that I get. Okay? I'm going to say this looks like it's a perfect power source, right? Because it's supplying as much power as it possibly can given its wave form that it has. Does that kind of make sense? So this is the phase difference between the voltage and current where you get maximum power transfer. Okay, so that's kind of interesting. What if I move on ahead and I look at see what happens when I get back to 90 degrees again? Now you might be able to guess, what kind of a circuit element do you think this is? This is an inductor, right? One of the ways that you know is that the current is lagging the voltage by 90 degrees. And how much power is being delivered on average? 0. Again, because an inductor, however much power it absorbs, it's going to give that back in a different part of the cycle. Okay? So anyway, I thought that might be interesting. If you want to kind of see what it looks like animated, it'll do that too here. But you can see how much power is being delivered shifts either to a positive amount of power absorbed to a negative amount of power absorbed, and that just happens as your phases between your voltage and current move relative to one another. Okay? So, any questions about this before I move into trying to explain mathematically a little bit better how to deal with this? Any thoughts or questions? Okay, let me move into this question. How do we multiply a voltage wave by a current wave to get power? Because we saw we can't just do phasor math like we were trying to do just a minute ago. We can't just multiply them in the calculator anymore. What we probably need to do is we probably need to actually do this in time domain. Okay? So let me just first collect some things here. What this equation becomes is just Vm Im. By the way, that's notation that is used in some sources to basically represent what is the maximum value that is reached for voltage, or what is the maximum value that is reached for current. Sort of, I think in here we may have even called that Vp and Ip at one point, like for peak, right? V sub m, I sub m is kind of getting at the same thing. It's however much you reach maximum. It's kind of an amplitude, if you will, if you think of it relative to the wave. Anyway, that gets multiplied by the cosine of omega t plus theta v. Theta v is the phase angle for the voltage, multiplied by the cosine of omega t plus theta I, where theta I is the phase angle for the current. Right? So all I did there was I collected together Vm and Im, and now I've got cosine of one angle multiplied by the cosine of another angle right next to it over there. And you know, I'll go ahead and be honest with you. I don't typically remember very many trig identities, right? I usually have to go look up what's, you know, maybe in a table of trig identities or something, look up a trig identity that might be useful. So I did that, and I looked up this one. Okay, there is a trig identity that says that the cosine of alpha multiplied by the cosine of another angle beta is equal to 1/2 of cosine of alpha plus beta plus cosine of alpha minus beta. So this is just a trig identity. Now, knowing that trig identity, what can I do with my expression for power here? P is going to be equal to Vm Im multiplied by, I'm going to replace where I had cosine of one angle times the cosine of another angle with all of this stuff over here. So 1/2 of, tell you what, I'll pull that 1/2 out here. Put this over 2. And what I'll end up with inside over there is cosine of omega t plus theta v plus the angle that I have in the other one, right, is omega t plus theta I. And then to this, I'm going to add the cosine of omega t plus theta v minus omega t plus theta I, like this. So far, so good? Now, what do you notice happens over here with, I need one more parenthesis there. What do you see happens over here with this omega t in my second cosine function? That subtracts out, right? And so I can rewrite this thing to say this is going to be equal to, P is going to be equal to Vm Im over 2. What happens with omega t in the first cosine? I can probably collect those together. 2 omega t plus theta v plus theta I, right? And I missed my cosine function there, so give me a second. Put that in there. Plus the cosine of just simply theta v minus theta I. Now I want you to see something here. What I have with this first cosine is a function of time, right? And it looks like what? It's a wave, right? And how is that wave centered on the vertical axis? Just the front part of this, right? Just the first cosine, right? There's nothing that can allow that wave to shift off of where it's centered around 0. Does that make sense? There's nothing about that curve that allows the center of that cosine wave to be moving up or down relative to 0. That comes from the second part. This second part is a constant, right? And this accounts for the vertical shift off of 0. That make sense? So what is typically done here is we go, well, you know, we can use this directly if we want to figure out what this p as a function of t is. But what's more often useful about it is that we can say the average power is going to be equal to Vm Im, and we notice that the first term in this set of parentheses right here is 0 if you go for all time, right? So we can just ignore that first chunk, because if you go for all time and try to find an average for all time, that piece is going to go to 0, and all you're left with is the cosine of theta v minus theta I. And that gives you an expression for average power over a long period of time. Okay? What do you think about that? You want to do an example? Why not? Let's do an example.